Okay, so prepare for a bit of a cosmic curveball today. We've been digging into some brand new research about a planetary system, K2360.
Right, about 750 light years off. Orbits a star pretty much like our sun.
Exactly.
Hmm.
And what's really got me hooked is just how strange one of the planets is.
Hmm.
So our mission for this deep dive is basically to unpack the secrets of K2360.
Especially that unbelievably dense world.
Yeah, and figure out what it tells us about, how planets can evolve in these pretty wild ways. We're mainly drawing from a new paper in Scientific Reports.
And what jumps out immediately about K2360 is the sheer contrast between the two planets they've found there.
Okay.
So first you've got K2360b. It's what they call an ultra-short period super-Earth.
Super Earth, meaning bigger than Earth, but rocky.
Yeah, roughly 1.6 times Earth's size. An ultra-short period because it whips around its star in just 21 hours.
21 hours, that's incredibly fast.
It is, but here's the really weird part. For its size, it's incredibly heavy. It packs in about 7.7 times the mass of Earth.
Whoa, wait, 1.6 times the size, but nearly 8 times the mass.
Exactly, making it one of the densest planets of this type ever found. What does that kind of density, immediately suggest to you?
My first thought is something dramatic must have happened. I mean, the massive for its size, it's like it's made of, solid iron or something much denser than typical rock.
Right.
It really doesn't fit the standard picture of a rocky planet, does it? It makes me think maybe we're just seeing, like, part of the original object.
Precisely. And that leads right into the main hypothesis. K2360b might actually be the stripped-down core of a much larger planet.
Like its outer layers got removed somehow.
Kind of like, peeling an orange and just leaving the inside. One of the co-authors, Davide Gandolfi, put it nicely. He said, this planet gives us a glimpse into the possible fate of some close-in worlds.
Where only the dense rocky cores remain.
After billions of years of evolution.
Exactly. It really drives home that planets aren't static things. They change, sometimes radically. Wow. Okay, so what could possibly strip away a planet's outer layers like that? It sounds pretty violent.
Well, the main suspect here is the environment itself, being so incredibly close to the star. Remember, its year is less than one Earth day.
Yeah, 21 hours.
It's just constantly blasted by intense radiation from the star. Think of it like a relentless stellar wind, or maybe like a giant hairdryer.
Okay.
Just blowing away the planet's atmosphere and maybe even some lighter mantle material over billions of years. It's a process called photoevaporation.
Photoevaporation. So the star's light and heat literally boil off the outer parts.
Over immense timescales, yes, that could definitely strip away a huge chunk of its initial mass, leaving behind just that super dense core we see now.
That's a vivid image. The star essentially cooking the planet down to its core. And the research mentioned how they figured this out, right? Using both transit measurements and radial velocity data.
Correct. Those two techniques are key here.
Can you walk us through how they work together?
Sure. So when K2360b passes directly between us and its star, that's the transit, it blocks a tiny bit of the star's light.
Like a mini eclipse.
Exactly. We see a small dip in the star's brightness. By measuring how deep that dip is and how long it lasts, scientists can figure out the planet's physical size and how long its orbit takes that 21 hours.
Okay, so transit gives us size and orbital period.
Sure.
What about the mass? That's the radial velocity part.
Right. That uses the star's wobble. As the planet orbits, its gravity pulls on the star, making the star move back and forth just a tiny bit.
Like planets tugging on our sun.
Precisely. We can detect this wobble by looking for tiny shifts in the color of the star's light, the Doppler effect. You know, like how a siren changes pitch?
Ah, okay.
By measuring these shifts, we can calculate the mass of the planet doing the pulling. So transit gives us size, radial velocity gives us mass.
And if you have both size and mass,
you can calculate density, mass divided by volume. And in K2360b's case, that density came out exceptionally high, pointing strongly towards, an iron-rich composition, just what you'd expect for a planetary core.
Got it. So K2360b is this super dense survivor, maybe a former gas or ice giant's core that got stripped bare. But it's not alone, right?
Yeah.
There's this other planet, K2360c.
Yes, the outer companion. And it seems crucial to the story.
How does it fit in? How could it have influenced the inner planet to end up like this?
Well, this is where things get really interesting dynamically. The idea is called high-eccentricity migration.
Okay.
Based on simulations run by another co-author, Alessandro Alberto Trani, K2-360c, which is more massive.
How much more massive?
At least 15 times Earth's mass, though we don't know its exact size because it doesn't transit.
Okay, a hefty neighbor then.
Definitely. So its gravity could have interacted with K2-360d in the past, maybe through orbital resonances or close encounters.
Like giving it a gravitational kick.
Exactly. A kick that could have thrown K2-360b onto a much more elongated or highly eccentric orbit. As Tranny said, their models show K2-360c could have pushed the inner planet into its current tight orbit through high-eccentricity migration.
So K2-360b wasn't always scorching hot and orbiting in 21 hours. It started further out, maybe on a really stretched out path, like an oval.
That's the idea. It got flung onto this wild elliptical path, and then once it was on that path, another process became really important: tidal forces.
Tides, like the moon and Earth.
Similar principle, but much stronger because it was getting so close to the star on parts of that elliptical orbit. The star's gravity would pull harder on the near side than the far side, stretching and squeezing the planet.
Okay.
Over a long time, these repeated tidal forces act like a brake. They tend to circularize the orbit, make it less elliptical, and also shrink it, pulling the planet closer and closer to the star.
Until it ended up in this stable but tiny circular 21-hour orbit we see now.
That's the most likely scenario they modeled, yes. A combination of a gravitational nudge from the outer planet, followed by tidal forces circularizing and shrinking the orbit.
That's quite a journey. From a potentially normal start to a wild elliptical ride, ending up as a stripped core hugging its star. The paper also mentioned, briefly, something about spin-axial tilt as another possibility.
Ah, yes. That's another factor that could play a role in tidal evolution. If a planet is tilted significantly on its axis, like Uranus in our solar system, the way the star's tidal forces act on it can be more complex. It can affect both the orbit and the planet's rotation, potentially also helping to drive it inwards and circularize the orbit.
So it's another way tides could have worked on it, depending on its initial tilt.
Exactly. It's acknowledged as a possible contributing factor. It just shows there are often multiple physical processes at play, and disentangling them is, well, tricky.
It sounds incredibly complex, piecing together this history. How do scientists, like Tranny's team, actually reconstruct this? It feels like trying to watch a movie backward with most of the scenes missing.
It is a bit like cosmic detective work, yeah. They basically start by making educated guesses about what the system might have looked like early on.
Like where the planets formed, their initial masses, their orbits.
Right. Plausible starting conditions. Then they use powerful computers to run simulations, essentially. They build virtual models of the system and let the laws of gravity play out over billions of simulated years.
They run it forward in time.
Yes, many, many times, each with slightly different starting parameters. They're using our understanding of physics, like how gravity works, how tides work.
So it's not random guessing. They're testing physically plausible scenarios.
Definitely. Our knowledge of these key evolutionary mechanisms, like tidal migration, helps guide which initial conditions are worth testing. They aren't just, throwing darts.
Yeah.
And then the crucial step is comparing the results of these simulations, the final predicted orbits, masses, stability of the system, with what we actually observe today with our telescopes.
So they see which simulations end up looking like the real K2-360 system.
Exactly. If a simulation produces a system that matches the observations and stays stable, it suggests that the initial conditions and the physics included in that model might be a good reflection of the system's actual history. It's about finding the best fit for the evidence.
That's like running thousands of experiments to see which one matches reality. The article calls K2-360 a valuable toolbox or laboratory. Why is it so useful for planetary science? What makes it special?
Well, a few key things. First, like we discussed, we can measure K2-360b with both transit and radial velocity.
Getting size and mass.
Right. That dual detection is relatively rare and incredibly powerful. It gives us that precise density measurement, which tells us so much about its likely composition that it's probably this iron-rich core. Many exoplanets we only detect one way or the other, so the picture is much fuzzier.
Okay, so the good data on Planet B is one reason.
Second, the very fact that there is an outer planet, K2-360c, is huge.
Because it allows for those interaction scenarios.
Exactly. It gives us a concrete way to test theories about how planets interact and migrate. If K2-360b were alone, explaining its bizarre density and tiny orbit would be much more speculative. We might still guess photoevaporation, but we wouldn't have this strong hint that gravitational pushes from a neighbor were likely involved.
So the companion provides context, and allows testing of more complex formation theories.
Precisely. It really highlights that you often can't understand a single planet in isolation. You need to see it as part of a system, understanding the dynamics between siblings. Studying these multi-planet systems is crucial.
That makes a lot of sense. It's the interplay that holds the clues. So, thinking ahead, what does this research mean for, future planetary modeling? Are our current tools good enough?
Well, it definitely points towards needing even more sophisticated models. The researchers specifically mention the need to better integrate photoevaporation, that atmospheric stripping by the star, directly into the models of tidal migration. Right now, they're often treated a bit separately.
So combine the effects of the star's radiation and the tidal forces in the same simulation.
Exactly, because both are likely happening simultaneously for a planet like K2360b. Doing that should give us a much better handle on how both the mass and the radius of these close-in planets change over billions of years.
Because the tides are changing the orbit and the radiation is changing the mass and size.
And those things probably affect each other. So merging those effects should paint a clearer, more accurate picture of how planets like K2360b actually evolve.
Makes sense. It's about capturing all the interacting physics.
Right. And then the big goal is to apply these better, more comprehensive models to all the new exoplanets we're discovering.
To see how common systems like K2360 are.
Exactly. Are stripped cores like K2360b a dime a dozen around sun-like stars? Or is this a really rare, unusual outcome? Answering that tells us a lot about the general pathways of planet evolution.
Okay, so summing up our deep dive into K2360.
Yeah.
We've got this system with an incredibly dense inner planet.
K2360b.
Very likely the exposed core of a much larger planet that lost its outer layers, now orbiting its star in just 21 hours.
And the evidence really points to its neighbor, K2360c.
The outer, more massive planet.
Playing a key role through gravity, maybe nudging it onto a highly eccentric path where tides then took over and dragged it inwards.
It's not just a story about two weird planets, is it? It really gives us a framework, a case study for understanding how dynamic and, frankly, sometimes violent the lives of planets can be.
Absolutely. It's a fantastic reminder that planetary systems aren't just static museum pieces. They're evolving, interacting, changing environments shaped by gravity and their stars over cosmic time. K2360 is a great real-world glimpse of those processes.
And it really does fire up the imagination, doesn't it? I mean, if this kind of extreme transformation can happen, what other truly bizarre planetary setups are out there?
Things we haven't even conceived of yet.
Exactly. What other fundamental processes shaping planets are we still missing? What else is waiting to be discovered that could completely rewrite our understanding? It's pretty humbling, really.
And exciting. There's still so much to find out.